Remembering our teams get 5 minutes to prepare, so that please keep the noise down so they can prepare reasonably carefully, and then when they are ready, they can start. So to start the second stage, Poland, you have 5 minutes to prepare. Okay, team from Poland.
Good morning, ladies and gentlemen. My name is Anna Wale to represent Poland. I would like to show you our solution to task number 5, 2 balloons. It is known that air in 2 partially inflated balloons will flow in different directions depending on initial balloon's volumes. We had to investigate this phenomenon. Please firstly take a look on these 2 videos. The initial volumes seem to be quite similar. However, in the first case, the smaller balloon is pumping the bigger one, and in the second one, the 2 balloons are becoming equal. So, it is of note that the air will flow from the higher pressure to the smaller pressure, and therefore, the pressure inside the balloon will be a key parameter in our system. When I try to pump a balloon, firstly, it is very hard. Then, it is becoming easier. The balloon is becoming bigger and bigger. When it's very large, the surface is very stiff, and it's hard to pump it again. We describe the pressure inside the balloon depending on their sizes. assuming that balloon is spherical and also that the pressure inside depends only on volume. And it turned out that in small balloons, the pressure will be high because the pressure decreases with radius squarely, and additionally, in big balloons, we obtained high pressure because the pressure would be proportional to the stiffness of the surface. What is obvious, what will happen if we don't have the equal pressures in the system. However, this condition do not describe what will happen if we have the same pressures in the balloons. The point is that with small deviations in pressure, the system have to come back to its equilibrium. So it turned out that in the case of two small balloons, when we deflate smallly one of them, it will generate a much higher pressure and will pump the other balloon. And in case of two big balloons, when we smallly deflate one, it will generate smaller pressure and it will be pumped again. So to derive on which volumes we have this two situation, we had to assume that volume is constant. Why volume is constant? We estimated how the pressure will compress maximally in a balloon, and it turned out that would be about 2%, as you will see in a minute. Okay, so here you can graph. Okay, so the next step in our research would be determining the stiffness of this rubber. To think about the physics of it, we have to look at the molecular structure of the rubber. Rubber is built of chains of polymers connected in nodes. Between these nodes, single molecules can oscillate freely without interaction with other molecules. And they oscillate with temperature. These oscillations cause the movement of one molecule's end. In case of unexpanded state of rubber, the movement of all these molecules do not affect the movement of whole net because they are random. However, if we expand the rubber in one direction, it would be more probable for the molecule to come back to its equilibrium rather than to go further. And because of that, the certain force occurs. To somehow calculate this force, we have to use the first law of thermodynamics for the rubber. We assume that because there's no interaction between molecules, the internal energy depends only on temperature. And the internal energy, the change of it, will equal the heat delivered to rubber. We assume that the process is reversible, the volume work, and also the work connected with stretching the rubber. However, we know that from many works, for instance from the trellis work, that the volume do not change greatly with elongation. And because of that, we erase the volume part. Also, our process is quite slow, and the temperature do not change considerably, and because of that, we also assume that it is isothermic process. And with that, we can derive a conclusion for the force stretching the rubber in case of isothermic process. So this force will be proportional to the temperature and to the change of entropy with radius of the balloon. The entropy somehow describes the arrangements of the molecules. So in case of unexpanded state, the molecules would be orientated somehow randomly. However, if we expand balloon, they would be more oriented, and because of that, the entropy would be lower. To calculate it, we use a statistical definition of entropy, and additionally, we took the probability of our molecules, how they will be distributed. If we have a stiff, the soft material, when it's not expanded, it has more possible states to make rather than it is expanded. And we assume that the distribution of length in one coordination of these molecules, it's a Gaussian distribution. And integrating this distribution, from that we derive at this conclusion, this equation for entropy. Knowing the elongation of the rubber in all three directions, we can derive finally the change in entropy with elongation, respectively, to a constant. So we derived the force tension in the rubber, how it looked like, and also how the pressure inside the balloon will look like with radius. And from that, we can finally derive the equation for the pressure inside the balloon changing with elongation of the radius. However, we can see clearly here that there is a decreasing in pressure, which is inconsistent with our preliminary observations. So to check it, we come up with an experiment. We take our balloon, we attach it out to a manometer, the water manometer, and looking at the differences of height in pool of water, we looked what's the pressure inside the balloon. We pumped it in a compressor. We met with some obstacle during this experiment. Because the pole of water has certain inertia, we had such sinusoidal line. However, we know that the pole of water is a harmonic oscillator with damping. And subtracting the movement of pole of water to this equation, we can derive the pressure inside the balloon. And also, we needed to know how the volume is changing in time. And so to do that, we looked through the camera to our balloon. We fitted an ellipsoid to it. And then, assuming that the balloon is spheroid, we derived the volume. So here you can see the raw data, the experimental data after subtracting the initial pole of water, and our fitted theory, and it is a certain inconsistency in the last part. It is because in a long extension, our assumptions do not hold well because the certain stiffness occur in the rubber. I will introduce you two sources of this stiffness. Because in the high entanglement, the molecules interact with each other more, there is, the force generated is higher. For instance, if the molecules are elongated, in case of unexpanded case, it do not have much influence. However, if we expand our molecules, the certain stiffness occur due to this fact. Additionally, in unexpanded state, rubber is quite isotropic. When you extend it, the crystallization occurs, which additionally causes a stiffness. So to have an analytical solution with this correction, we taken the polynomial correction from the work of Jan Lewin to rubber balloons. And you can see clearly that with this correction, the pressure is increasing. We fitted the theory to the several balloons, and it fitted pretty well. So we made 5 experiments with the same type of balloon. And here you can see this pink area. It's a standard deviation of these measurements. And from these measurements, we could derive the coefficients which would describe our rubber. And with these coefficients, knowing how exactly how the pressure changes with the volume, we can finally derive the diagram, what will be the flow, direction of the flow into the balloons, depending on the initial volumes. So because of the symmetry of the problem, because we have the same balloons, I will talk only about the half of it. The lines symbolize the fields when the pressure inside the balloons are equal. However, the red lines when this state is stable, and the blue when it's unstable. So that means that in red field, the small balloon will pump the bigger one, and in the green field, the big balloon will pump the smaller. We conducted another experiment to check whether our theory predicts it well. We attached the second balloon to our system. We made a photo of two balloons. Then we released the air, and we made a second photo. However, we have to keep in mind that the different balloons are not the same. I mean, if we are using one balloon several at a time, it's wearing out, and because of that, for each experiment, we will take a new balloon. So here you can see 72 experiments. For each, the pair of two balloons was taken. And the red points symbolize the flow from smaller to bigger balloon, and in the reverse in the case of green points. So to sum up, we described qualitatively why the pressure is big in small and big balloon. We explained the forces occurrence by molecular structure of the rubber. We derived the pressure equation. We changed it experimentally. And we finally derived a graph which answers the question.
Okay, thank you. Have to stop you
Thank
there.
you very much.
And we move straight on to questions from the opponent. But again, can I ask you to introduce yourself?
Good morning, ladies and gentlemen. I'm Suranaree from Singapore, and now I'll oppose problem 5, two balloons. So, moving on to the clarification questions to the reporter, can we go to slide 16? You show a graph of, I think, pressure against time, is it? Yeah, so, volume, okay. So, is this typical experiment run data?
Can you repeat the question, please?
Is this one of your experiment results for this graph?
Yes, it's one of my experiments.
So you inflate across, say, 0 to 6 liters, right? The unit is liters. What is the unit for volume?
Okay, so this was the liters.
Okay, thank you, liters. Can we go to slide 72 with your phase diagram of, slide 25, yes. So for these balloons, are they the same balloon or are they different balloons for each dot? So.
Okay, the different balloon from the same package. So they had the same properties.
Okay, so different balloons, thank you. Can we go to slide 13? 13. Yeah, so this is a theoretical plot of from the Gaussian distribution, right? So
yes.
The pressure goes up. Okay, thank you. Can we go to your earlier qualitative explanation? So is the cause of the two balloons phenomenon because the pressure radius curve has increases and decreases and goes up again?
Yeah, it is essential.
Okay, so we have to have this curve, this going down, then coming up, right?
Yes, to have these regions.
Okay, thank you. Can we go to slide 19? You quoted from literature a correction factor. So is there any physical basis for this factor?
Could you repeat the question?
Is there a physical basis for this correction?
Okay, so this is
Very quick answer, please. We are out of time. Very quick answer.
So this polynomial correction, it do not have any physical basis. Such corrections are widely used by scientists because it's very hard to derive a theoretical solution for this non-ideality of the rubber.
Okay,
Thank you.
That's fine. Move on to preparation, please. Okay, that's time.
Good morning, ladies and gentlemen. I am Shen Yujun from Singapore, and I'll now oppose two balloons. So we take a look at the problem statement, and we note that based on the initial volume condition, we must be able to predict the direction of airflow. So this is the key of the problem. Moving on to the summary of the report. First, the reporter considered the stress-strain relationship of rubber from first principles and was able to then characterize a single balloon, and using that, she moved on to verify the phase diagram for two balloons, hence the phenomenon. So here is an overview of the strengths and weaknesses of the theory. I believe that she has accounted for the non-monotonous pressure radius curve using entropy, and it is this basic physics of the curve that allows for the two balloons to happen, because at the same pressure, we are able